Imagine a star so dense that it's heavier than our entire sun, yet it's incredibly small, a real cosmic paradox. This is the reality of a newly discovered white dwarf known as WD0525 plus 526, which is challenging our current understanding of these celestial objects. But here's where it gets fascinating. This ultra-massive white dwarf is believed to be the result of a merger event in its past, leaving behind a unique signature that sets it apart from other white dwarfs. To grasp the significance of this discovery, let's delve into the world of white dwarfs and explore what makes them so intriguing. White dwarfs are essentially the remnants of stars like our sun or those with masses up to a few times that of the sun. When these stars exhaust their fuel, they expand into red giants, fusing helium until they run out of energy. At this point, they shed their outer layers, leaving behind a dense, hot core, the white dwarf. Most white dwarfs have masses around 60% of the sun's mass and gradually cool over time, as their heat source is the result of core collapse rather than ongoing fusion processes. However, recent observations from the Gaia spacecraft have revealed a population of hot, old white dwarfs whose heat is generated by a crystallization process within their incredibly dense interiors. Among these, 6 particularly massive white dwarfs caught the attention of astronomers, as they showed evidence of carbon in their atmospheres, suggesting they were the product of merger events. But WD0525 plus 526 is different. Despite its massive size, it lacks the carbon features seen in optical observations. So what's behind this anomaly? The answer lies in its extremely thin outer layer of hydrogen and helium, a staggering 10 billion times thinner than expected. This unique feature is thanks to the Hubble telescope's ultraviolet capabilities, which allowed researchers to detect carbon and infer that WD0525 plus 526 is indeed the result of a merger event, albeit one that produced structural differences in the resulting white dwarf. As Dr. Snehalata Sahu, co-lead author of the study, explained, "We are not able to explain it with other scenarios." The team believes that the white dwarf is not undergoing full convection, preventing carbon from escaping and being seen in optical observations. Instead, there's a semi-convection process occurring beneath the incredibly thin hydrogen and helium layer. But what could have collided with the original white dwarf to produce this object? The leading simulations suggest it might have been a subgiant star, but many uncertainties remain, and the researchers are hesitant to commit to a specific scenario. As study co-leader Antoine Bedrad noted, we would like to extend our research on this topic by exploring how common carbon white dwarfs are among similar white dwarfs, and how many stellar mergers are hiding among the normal white dwarf family. This research has significant implications for our understanding of white dwarf binaries and the pathways to supernova explosions. The discovery of WD0525 plus 526 highlights the importance of ultraviolet observations, which would have been impossible without the Hubble telescope. However, with Hubble nearing the end of its life and the next generation of UV telescopes, such as NASA's Ultraviolet Explorer, not launching until 2030, the team is urging the development of new instruments to continue this vital research. As Dr. Sahu emphasized, Hubble is going to die. We know that its instrument is coming to an end, so we have to think about the next generation UV telescopes. The study, published in the journal Nature Astronomy, raises thought-provoking questions about the formation and evolution of white dwarfs. What do you think is the most significant implication of this discovery? Do you agree that the development of new UV telescopes is crucial for advancing our understanding of the universe? Share your thoughts in the comments below.